So let me now kind of talk through the anatomy of some of these basis sets and what goes into them, okay? So let's talk about STO3G. We've already talked about this. We've said it's a minimal basis set, so there's one basis function per orbital that you would find in the actual atom. And it mimics a Slater-type orbital, but it's not Slater-type orbitals. It has contracted Gaussian-type functions, and each basis function is made out of 3 primitive Gaussians. So what does this look like? Here we go. Here's an example for a hydrogen atom. So this is in the format of the famous Gaussian program, and that format has been adopted since then by other quantum chemistry programs. So this is a common format. You put the name of the atom, and then there's a 0. I don't know if this is ever different than 0. Then you have one of your basis functions. So this is an S function, and it's made out of 3 primitive Gaussian-type orbitals. And each of those Gaussian-type orbitals then has 2 numbers associated with it. So there are 3 primitives, and then there are 3 lines that come after that. So each line is a primitive. And the first number is your exponent, so your zeta. So that tells you how tight or loose is this orbital, or how big or small it is. And an exponent of 3 means it's reasonably close to the nucleus. And for hydrogen atom, it's only got 1 proton, so it doesn't draw things in super, super close. So this is reasonable. And then you see it's got 2 other exponents where this is a much bigger orbital and this is an even bigger orbital. And I pre-contract these 3 Gaussians to best represent the shape of a Slater-type orbital. So these are my contraction coefficients, and these are fixed. These do not change. The user doesn't change them, and when I do the Hartree-Fock procedure and solve for the molecular orbitals, they still don't change. They're like an inner summation, and they are fixed. What would change is the exponent, is the coefficient outside of this basis function. But I would have other basis functions for other atoms, and I would mix and match those. Let's talk about STO3G for a carbon atom. So for a carbon atom, I put the symbol, and I got a 0. So there are now 2 sections in my anatomy here, in my basis set file. The first section describes the carbon 1s orbital, okay? And that is described by 3 Gaussians because it's STO3G. And here you see the exponent is much bigger. So in carbon, the 1s orbital can be much, much closer to the nucleus than it is in hydrogen because the carbon has a much bigger nuclear charge. It has a nuclear charge of 8 instead of 1 for hydrogen. So the exponents are bigger. I still have a range of them though. I have a very tight one and then a less tight one, and then this one was about the same size as the tightest one in hydrogen. And they have fixed coefficients in front of them, and these coefficients again are chosen, and the exponents are chosen to mimic the shape of a 1s orbital, Slater orbital in carbon, but made up of 3 Gaussians. In carbon, I have a 2s function, and I need some 2p functions. So how are those described? Well, your 2s function and your 2p functions, this is a quirk of the STO3G basis set and some of the Pople basis sets. The 2s and 2p functions both share a common set of exponents. So notice the 2s and 2p, the exponents are much smaller than 1s. That's because the orbitals are bigger because they're valence, so that makes sense. And there's again a range of them. Some are tighter, some are looser. Your second column is the coefficients in front of each primitive Gaussian function to make up the 2s function. So the 2s function is primarily, let's see, that's e to the minus 1, so that's really 0.09. The biggest coefficient here is 0.7. So it's 0.7 of this guy, so it's a little bit bigger. And then with some weight for these tighter functions, that is the combination that makes up your 2s function. And then this third column is the exponents that make up your 2p's. And the 2p's have a slightly different combination than the 2s does, but they share a common set of exponents. That's unusual. Normally, your p's and your s's have different sets of exponents, but that's a quirk of some of the Pople basis sets. And sometimes these are called SP shells or SPE shells, meaning they have a shared set of exponents here for S and P. Okay? And these Pople basis sets, well, of course, they're named after John Pople, the Nobel laureate, who created the Gaussian set of programs. STO3G, I've already mentioned, is a minimal basis in which each atomic orbital is represented by 3 Gaussians to mimic a Slater-type orbital. Okay? Now, he has more than just minimal basis sets. So let me introduce you to 631G, and this will help us understand the split valence ones a little better, okay? So it's split valence, meaning the core has one basis function describing it, and then the valence, it's a split valence double zeta, so the valence functions, each atomic orbital in the atom is described by 2 basis functions. And I'll show you what the 6 and the 3 and the 1 in the G mean in a second. Well, the G means Gaussian. Okay, so I'll already tell you that. But the core is going to be made out of 6 primitive Gaussians contracted to a single CGTO. And then the valence is going to be made out of 2 functions. One function will be a linear combination of 3 primitive Gaussians. And then the other function will just be 1 Gaussian function. Okay? So we'll see this on the next slide. But by the way, you pronounce this 631G. It's not 631. There's no 31 anything. There's a 3 and there's a 1. Okay? So that's sometimes how you tell if somebody's new to computational chemistry or not. If they call this 31, it means they don't have so much experience. There's no 31 involved at all. It's a 3 and a 1. Okay, so here it is. I hope this will make sense. This is the same format we've been looking at. You've got a 1s function, which is a linear combination of 6 primitive Gaussians. Here they are, 1, 2, 3, 4, 5, 6. Some of them have extremely tight exponents, so that's really wow, that's a big one. But it has a low weight in front of it. And then you have a range of ones that get looser and looser, but they're still sort of tight. So 3 is, it's not very loose. And it's describing a core electron, so that makes sense. So I've got this linear combo, and this fixed linear combo gives me a single contracted Gaussian type function that describes the carbon 1s in whatever molecule I throw this carbon into. Then I have the valence functions. What do I need? I need something to describe the 2s. And because it's a double zeta basis set, there are 2 functions. So here's the first one. The 2s is going to be a combo of 3 Gaussian type functions with these coefficients in front of it. Okay? And the 2p will be the same exponent functions, Gaussians, but with a different linear combination of them, different mixing of them. And because it's double zeta, I need a doubling of the functions to describe the 2s and the 2p. So that's what this final line is for. Here is another 2s function. If you like, you could call this one 2s, and call this one 2s prime or something. And this one is a bigger function, so in case the atom wants to respond somehow to its environment by shifting into a slightly bigger orbital, it has a bigger basis function available to do that. And because there's only one of them, the coefficient in front of it's just 1, obviously. And again, the exponent is shared between this extra 2s and this extra 2p function because it's a Pople basis set. Okay. Now, I showed you 631G. Popular is 631G star, also known as 631G Princess D. What is this star? What does that do? And what does the Princess D do? That's what happens if you have 631G, but you add depolarization functions on the non-hydrogen atom. So if you got like a carbon atom, I add a set of d functions, and I always get a complete set of them. So I get 5 of them, or 6, depending on whose program you're using, or if you're being historically accurate or not. If I want to polarize the hydrogen atoms, well, hydrogen occupies s orbitals, so to polarize that I need to go up 1 in angular momentum, so I need a p function. So that's called 631G star star. So the second star means I add p functions to hydrogen, or it's also called 631G d comma p. The stars are the old school notation. The Princess D or Princess D comma p is the newer notation. I guess the newer one is a little better because it's more obvious what kind of functions you're adding. Although you still have to remember that whatever comes after the comma is added to the hydrogen, but anyway. Yeah. Okay, 6311G is a triple zeta basis set. It's just like the previous slide, except I would have one more row where I would add one more primitive Gaussian function to give me a third 2s or 2p function. Okay? What about this plus thing? Sometimes you see things like this, 631 plus g. What is that? The plus indicates diffuse functions, those bigger functions, in case I have anions or I need more accuracy for polarizability or whatever. So 631 plus g is 631g, where I add diffuse s and p functions for non-hydrogen atoms. Like carbon would get an extra diffuse s function and a set of diffuse p functions. What if you wanted to add diffuse functions to hydrogen as well to get a little more accurate? Well, that's called 631 plus plus g. So the second plus means I add diffuse functions on hydrogen, just like the second star means I add extra polarization functions on hydrogen. Sometimes you'll see something like this, 6311G, Princess, 3DF, 2PD. What is that? The stuff in Princess here, again, like it was up here, is the polarization functions. So this would be a triple split valence, triple zeta basis set, where the core is described by 6 primitive Gaussians, but giving me 1 contracted Gaussian type function. Then I would have 3 functions describing the valence. One of them is a contracted Gaussian type function made out of 3 primitives, and then the other 2 are just primitive Gaussians. And then on top of that I add these polarization functions. So the stuff before the comma is non-hydrogen atoms, so I add 3 sets of Ds. That's a lot, right? So there's a lot of polarization going on. And I get really elaborate and I go ahead and add a set of F functions even to describe the polarization. So this gives me good flexibility to describe polarization. And then after the comma is what I do for hydrogen. I add 2 sets of P's and a D function. So this is a pretty darn big basis set, although there are bigger ones. Now let me talk a little bit about how you name, or how you designate the number of functions in a basis set. Okay? So hydrogen atom, if it's a minimal basis, then we know that hydrogen atom normally involves a 1s function, and in a minimal basis set, that means I'll add 1 function, and it'll be s-like, but okay. So I have 1 function, and it's a s-type function. Okay, so you could call that 1s. What else would you call it? Carbon atom in a minimal basis. Well, in the actual atom, I involve 1s and 2s and a set of 2p's. So I could write this way. 2 s's, so in this context, this doesn't mean a single 2s function. It means I have 2 s functions, a 1s and a 2s. And 1 set of p's. So anytime you have a set of p's, you just call it 1p. It means 1 set of p's. Okay? So that's 5 functions. Why is that? Well, there are 2 s's. Each s function is a function. So there's 2 functions from the s's. And then 1 set of p's, but for p to have a set, I need px, py, pz. So px, py, pz. So that's 5 functions, okay? And that would be a minimal basis. What if I had a true double zeta basis set? Double all that. So instead of 2 s's and a set of p's, I have 4 s's and 2 sets of p's. And if that was 5 before, then obviously it's 10 now. Again, normally you don't really double everything because the core is perfectly adequately described by a single function. So instead of really doubling it, I will take that 1s and just use it, not double him. The 2s, I'll double him and make another one, like 2s prime. And then my set of p's, I'll have like 2px, 2py, 2pz, but then I'll double those and have like 2px prime, 2py prime, and 2pz prime, and now I'm up to 9. So there are 3 s functions, 1 for your core and 2 for the valence, and 2 sets of p's for 9 functions. And really, to get this number of functions, you just take each number and then multiply it by how many functions are inside your symbol. So an s has 1 function, so 3 times 1, plus a p is a set of 3 things, so 2 times 3 is 6, plus the 3 I had before gives me 9. Now let me say a little bit about, I've talked about the Pople basis sets for a minute. Let me say a little bit about the Dunning basis sets. So these were invented by the famous Tom Dunning in '89 and some subsequent papers as well. And what he realized is that the old basis sets were invented to give you good basis sets for doing Hartree-Fock calculations. But they weren't really well designed for doing post-Hartree-Fock electron correlation calculations. And in the late 80s, we were getting computers fast enough for small molecules where we could easily do CI or MP2 or even couple cluster calculations. And so he said, you know what, the basis sets we have maybe are not the best for those kind of calculations. So he invented what he called the correlation consistent basis set so that you could do electron correlation calculations. And he used CISD when he was inventing them, which ought to be adequate for the purpose. And his basis sets are named things like this: CC-PVXZ, correlation consistent polarized valence X zeta. So they're designed to be good for correlation calculations. That's what the CC means. P means you always are going to polarize them, so there will always be polarization functions. X is going to tell you, is it double zeta or triple zeta or whatever. So it'll be D or T or Q or 5 or 6 or 7. And Z just means zeta. Okay, so that's what this symbol means. Again, this is a beginner's mistake. If you have a beginner at computational chemistry, they can't remember exactly how this is spelled, and they'll get the capitalization wrong, and they'll make the P capital. And that means it's usually somebody who's either forgetful or maybe new to computational chemistry. All right, so the philosophy of this set of basis sets is that to converge smoothly to the infinite basis set limit, we're going to add functions in shells. Let me explain what I mean by that. So for carbon atom, a correlation consistent polarized valence double zeta basis set is going to be this in the style of the previous slide: 3s, 2p, 1d. So again, that means 3 s functions, 2 sets of p's, and 1 set of d's. And you see there's a pattern here. There's 3 of these, 2 of those, and 1 of those. That's kind of what I mean by like the shell structure of this. And does it make sense this is double zeta? Well, I hope so, because it's a split valence basis set, so there's only one function for the core 1s, so that gives me 1s function. The 2s is described by 2 functions, like 2s and 2s prime, so that's a total of 3 s functions: 1s, 2s, and 2s prime. That's your 3s. Carbon atom involves a set of p's, obviously, and because it's double zeta, I have 2 sets of p's. That's where the 2 p's come from. And then it's polarized, and because I involve p functions, then to polarize that, I need to jump up one more level and add a set of d's. So indeed, this really is a split valence, polarized valence double zeta basis set. To get to triple zeta, well, I would have 1s, and then 2s, 2s prime, and 2s double prime. And then likewise, a set of 2p's, and it's triple zeta, so 2p prime and 2p double prime. Okay? And the p functions are sets of 3's, but in this notation, so I would have 4 s's now, because I went from double to triple zeta, so I had to add one more s. 3 p's, it's triple zeta for the p valence. And then to polarize that, you might think, well, I'll just use another d function or whatever. No, you do the shell idea. So you add 2 d's, and then you add one more to go to an f. So I get the same pattern, 4, 3, 2, 1. Okay? Now you might think to yourself, this seems a little overkill in the polarization. And for some purposes, it turns out it is. And it's even worse than that, because 2 sets of d's, that's really 10 functions, right? Or depending on your program, maybe 2 times 6, 12, but usually 10. And then f, that's a set of 7 functions. So these polarizations are costing me a lot of functions that I'm adding. QZ, well, you can guess what that would be. Add 1 to all these numbers. 5s, 4p, 3d, 2f, 1g, because I went up 1. So now I'm adding a set of g functions. Oh my goodness, this thing is like crazy polarized. All right, but that's the basic idea of this. Now, do they always have this 5, 4, 3, 2, 1, structure? No. It depends on the element you're looking at and whether you added diffuse functions or not. And there's some other things that go into this. So don't let me overly convince you that it must always exactly follow this pattern. But this is just kind of the general idea of the shell structure. But if you do this, you do get nice convergence. If you go from double to triple to quadruple and do a series of calculations, your energies and your dipole moments and other properties will smoothly converge, which is really nice. Sometimes you'll see these basis sets with an AUG prefix, like AUG CCPVDZ. What that means is your basis set is augmented by a set of diffuse functions. And I add them again in the shell kind of structure. So I add a diffuse S, a diffuse P, and a diffuse D to CCPVDZ. Those are all the things I have in CCPVDZ. It consists of S's and P's and D's, so I add a diffuse set for each of those things that's in the basis set. Okay. Now, there are some other versions out there, so you might occasionally see July CCPVDZ or June CCPVDZ. These are named by Don Trular, where he said, well, you know what, AUG really means augmented, but let's pretend for a second it means August. And if I pretend that, it gives me a convenient way to name things. If I start chopping out some of those extra polarization functions, or extra diffuse functions, I should say, because adding a set of diffuse S, P, D, and F, depending on how far you have to go, it's usually overkill for most things. So you can cheat a little bit and say, you know what, I'll add diffuse S and P, but you know what, I'm not going to add diffuse Ds. Or maybe I won't add diffuse functions to hydrogen. And if you start making those approximations, then it's nice to have a convenient name for them. And so Trular gave us those names. So for example, July CCPVXZ is one step back from August, and that just says, you know what, don't put diffuse functions on hydrogens. What if that wasn't enough for you? What if you wanted to scale it back even more? Well, what comes before July? Well, June. And there in June, then you don't add diffuse functions to hydrogen, and you also take away from augmented the diffuse set with the highest angular momentum. So if I was in Aug CCPVDZ, I would normally add diffuse S, P, and D, but if I'm in June CCPVDZ, then those carbon atoms or other atoms that aren't hydrogen won't get the diffuse D either, and I won't add diffuse to hydrogen. So that gives you like a scheme to scale back and make these a little more affordable, but still have some diffuse functions. And normally S and P are the most important to have diffuse functions for. You will also sometimes see an extra letter C in these basis sets. So what if I had CCPVC? Well, I misspoke that already. It's hard to say these. What if I had CCPCVXZ? Okay, so there's an extra letter C. What does that mean? That means I add core correlating functions. So functions that are tighter and describe electron correlation motions near the nucleus involving the core functions, the core electrons. And if I want really high accuracy calculations, then I probably should include these. If I'm not freezing the core, meaning if I don't restrict core electrons to stay in their core orbitals when I do a CI or an MP2 or a couple cluster, then I really ought to have functions appropriate to describe where those electrons would dodge into, and that means I need these C functions. Okay? So if you're not freezing the core in your post-Hartree-Fock calculations, you probably should have these C functions. It's an extra set of functions, so the calculation will be more expensive because they have more orbitals, basis functions to go into it. A historical note, after the CCPV-XZ basis sets were invented and published and used, it was found that for your second row elements, your depolarization functions really were not quite tight enough. And so the basis set was revised, and that gave us the CCPV parenthesis X plus D Z basis set. So there's a plus D here. That tells you they added an extra set of tight D functions to sort of correct for the mistake in the original publication. And if you're doing, sulfur or something, you probably should be using these plus D versions of the basis set to get the best accuracy. Let me mention the Ulrichs basis set, or the Karlsruhe basis set. The most recent version is the set of def2 basis sets, and really this just means the second version of the definitions of the basis sets. And this is a more recent article that kind of captures this work, but there are earlier papers. This is a set of split valence basis sets, just like pretty much everything we've been talking about, except the minimal ones are all split valence. And they're named def2 something something. And smallest to largest, they go this way. So there's a whole list of these things. What do these mean? Well, the S you might think is single valence, like a minimal basis. No, they're really double zeta. So SZ, think of that, SV, think of that more as like split valence, not like single zeta or something. Split valence, parenthesis P means sometimes you polarize it and sometimes you don't, depending on the element. SVP means it's split valence and you definitely polarize it. You normally would want to do at least that. Split valence polarized in D. D means you sometimes add some extra diffuse functions here and there. They're not added in the systematic way that Dunning does, which honestly is kind of overkill, which is where we got the May and June naming to trim some of those out. So these diffuse functions are kind of more sparing, and sometimes it's S, sometimes it's P, sometimes it's D. It seems a little bit random to me where those diffuse functions come from. But this will be S. The SVs are basically double zeta. TZ is triple zeta, and P means it's polarized. So TZVP is kind of analogous to CCPV-TZ from the previous slide. D again means diffuse. PP sometimes means I add extra polarization. It kind of depends on what element you're talking about. And QZVP means quadruple zeta polarized. Quadruple zeta in the valence. It's still split valence, so it's still single zeta in the core. And so on and so forth. I think you see the pattern. So there was an earlier set called def-, and the def2s have now succeeded it. And I think I've walked through most of this, but just to recap similarities and differences, SVP is like CCPV-DZ, TZVP is like CCPV-TZ, although it has one more S for carbon, and QZVP is like CCPV-QZ, but it has two more S's for carbon. So they're similar-ish kind of to the Dunning, but sometimes they're a little more rich in the S and P space, and they're more sparing on the diffuse functions. Finally, let me tell you about some general considerations and what happens if you go to these bigger and bigger basis sets. So here's the convergence of vibrational frequencies for some small molecules in a paper I did a while back. And what I'm plotting is the error versus the complete or infinite basis set limit in the harmonic frequency for these diatomics. And on the x-axis is the size of the basis set. So these are the Dunning CCPVXZ basis sets. And this is double zeta, triple zeta, quadruple zeta, 5 zeta, 6 zeta. And you can see that I converge towards the complete basis set limit pretty rapidly, with the exception of double zeta. Double zeta can be off by 90 wave numbers or 20 wave numbers or 40 wave numbers, which isn't a giant amount, but it's kind of a lot if you're talking to spectroscopists. Triple zeta gets you plus or minus 20 wave numbers or so that's not bad. And then quadruple zeta, you're within a handful of wave numbers, and 5 and 6 zeta are essentially right on the money. So you do get a nice convergence. Double zeta, not always reliable, but then beyond that, errors start to get pretty small pretty fast. Same thing for bond lengths. These bond length errors for the same molecules, again, as I go double to triple to quadruple to 5 to 6 zeta, 0.02 something angstrom error is a little bit large. It's not giant, but it's not small. Triple zeta, though, gets me in the ballpark. I'm within a few thousandths of an angstrom, and then I'm almost exactly there by the time I'm at quadruple zeta, and 5 and 6 are basically exact. This is a really nice chart from one of Trygve Helgeker's papers that I like a lot. This is showing you normal distributions of errors for a set of bond lengths, where they were calculating the bond lengths with different methods. That's the different graphs. Versus what the exact answer is supposed to be. And so look at this upper left. This is CCPVDZ Hartree-Fock. And I forget what the scale is. These are like in picometers or something. So you can see it get this broad distribution. So there are some errors that are larger than 5 picometers. And the error distribution is shifted towards the left. So we tend to underestimate bond lengths with Hartree-Fock. And if I go to a bigger basis set, do I clean it up? No, I really don't. What if I go to quadruple zeta? No, I don't fix it. So Hartree-Fock, you're not going to get really accurate bond lengths, and it doesn't matter what basis set you use. So you might as well use double zeta, because why pay for quadruple zeta and make the calculation take longer when the results for bond lengths aren't any better? What about MP2? Well, the distribution is more peaked now, so that's pretty good. Double zeta is a little overestimated. Triple zeta is about right, although there are some errors, plus and minus. Quadruple zeta isn't necessarily any better. So again, there's like a magic trade-off of you want a basis set that's good enough for your method. For Hartree-Fock, it kind of doesn't matter. I'm not showing, STO3G, that wouldn't be very good. For MP2, triple zeta is definitely better than double zeta, but quadruple zeta isn't any better than triple zeta. MP3 people don't use much anymore. MP4, double zeta is not good enough. Triple zeta is better. Quadruple zeta is a little better than triple zeta. CCSD, you overestimate bond lengths with double zeta. You underestimate them with TZ, and QZ doesn't help any. So you might as well start at triple zeta, stop at triple zeta. CCSD parenthesis T gives you much more awesome predictions of bond lengths. Double zeta isn't big enough. Triple zeta is about on the money. Quadruple zeta is about the same as triple zeta. You could argue which one's better here for bond lengths. So there is a need to carefully choose your basis set so that it kind of matches or goes well with the theoretical method that you're using. It's not necessarily true that bigger basis sets are always more accurate. And you see a few examples here where it's not any better or sometimes even worse. So I'll wrap up then with some general comments. So I just said, the bigger basis set always better? Well, no, we saw some examples from the previous slide that that's not necessarily true. So STO3G, just don't use it. It's too small for real calculations. Honestly, if you've got molecules and they're not tiny, you probably can't afford something bigger than polarized valence double zeta. So 631G star, maybe 631G star star, or CCPVDZ, or the def2 SVP. That's the kind of basis set you'll normally be able to afford and that most people use. But if you've got anions or something like that, or polarization, you better put some diffuse functions on. If you are stopping at double zeta, in my experience, CCPVDZ isn't necessarily better than 631GD, P. However, the Dunning triple zeta basis set is definitely better than 6311G. So just don't use that one. Use the CCPVTZ. Sometimes your convergence can be disappointingly slow. I kind of showed you a couple examples where it looks like once you're in triple zeta, you're pretty darn good, and that often is true, but depending on the property, sometimes triple zeta doesn't quite get there, and then you have to go to quadruple zeta. That can be painfully expensive for the calculation, so it kind of depends on what you're doing. But if you're doing DFT, the silver lining is DFT tends to converge a little quicker with respect to basis set. So there, you more often can get away with a double zeta basis set or triple zeta. If you did quadruple zeta DFT, then you're pretty much getting towards the complete basis set limit for DFT. So that's good. That's what I just mentioned there. There's some nice papers about that by Angela Wilson. Check out this website, basissetexchange.org. This is a great resource if you need to download some basis sets for a particular problem. Most quantum chemistry packages come pre-packaged with a nice library of a lot of different basis sets. So you can just call up 631G star from quantum chemistry calculation from your quantum chemistry program and it's there. So that's really good. But sometimes if you have some elements that are less popular for computational chemistry calculations, you might find that the basis set isn't available in your program, but you might find it on this website, and you can download it in a format convenient for your program. So it's really, really great, and I advise it. Okay, well, I hope that gives you a good idea of what goes into these basis sets and some idea about which ones are appropriate for which problems.